And the work I'm going to present today, it's a joint work with Atila, Abdulkadiroglu. It's the market design for priority-based assignment with distributional objectives. Let me tell you what we are doing. It's a very it's very well known, particularly to this audience, that allocations of very high stake and high importance goods is done in a centralized way using preference and priority based assignment. And one of the success stories of market design and economic theory in general is that economic theorists understand the setup and have came up with solutions that advocated solutions for implementing this real life centralized assignment. And in particular, the success stories of deferred acceptance is well known, and it's been as the assignment rule for public school assignment, college admissions, and many other problems. What is less known in this, how to handle in this setup, is how to incorporate diversity in distributional objectives. I will argue that there is, in reality, the matching setup that we are considering for which we have these solutions does not fully correspond to the real life allocations. And in particular, we have limited theoretical understanding of how to assign mechanisms, how to design mechanisms when there are diversity in distributional constraints. This is a very broad question. This is a very broad topic, but let me make things a bit more concrete. I'm thinking of a particular assignment problem, the school as a choice, and there are oftentimes there's diversity in distributional objectives. The control school choice argues that for having purely preference and priority-based assignment may not meet the policy goals that we oftentimes have. In particular, we may want to have diverse student body, achieve balance in different dimensions, and we also want to give preferential treatment for underserved communities to high-performing and better schools. And two examples of distributional objectives in the school choice problem is one is the Chicago exam schools, where priorities are determined by the test scores. But on top of priorities, the Chicago public exam schools reserve seats for applicants from different tier groups. This population is divided into socioeconomic tiers, and 17.5% of seats are reserved for each of the four groups. The remaining 30% of the seats are not reserved for any of the groups. And the idea is that for these seats, the groups are giving preferential treatment so that the district can achieve its distributional objectives. Another recent example is the diversity in admissions reforms in New York City public schools. Mainly those exams or screened schools are using reserves where 25 up to 52% of the seats are reserved for applicants from a low-income socioeconomic group. The common solution in this setup is to modify the priorities of subsets of schools, those reserved for particular beneficiary groups, and then apply priority-based assignment to this problem. We may think of this and we may call it generally as a reserve rules. The goal in this paper is to provide an axiomatic foundations of using different rules, different mechanisms in priority-based assignment with distributional objectives. In particular, we ask specific questions. The reserves rule are very practically applied. They are well studied in the literature, but we are trying to understand the axiomatic foundations of the reserve rules. In particular, we want to come up with properties that reflect the natural desirable objectives of the school districts, which would characterize reserve rules as those that satisfy the axioms. And finally, in this setup, it's known that once we do this ad hoc approach of modifying priorities and assigning seats based on the updated priorities, the order in which we were going to process the different seats reserved for different groups would impact the final outcome and is consequential for the final assignment. Therefore, we ask which reserve rule should we use, and we find a positive result there. We show that the deferred acceptance mechanism, when all schools use a particular reserve rule, is the unique mechanism satisfying the axioms. There are a lot of terms here in the italics, like the set of axioms, particular reserve rules, and the axioms, which I'm not being concrete. And during this conversation, during this presentation, I will elaborate on what these results exactly mean. But this is the big picture of our project. I would, before jumping to the model and related literature, I would like to highlight one crucial difference of the methodological approach that we are taking, and that in the previous literature. I started the talk saying that there was very limited theoretical foundations for designing markets with distributional objectives. It may sound controversial because it's a very huge topic, and it has a very rich literature. And what we're going to argue that is that in the school choice problem, the way that literature handled the diversity and distributional objectives does not follow the axiomatic approach, and may not clearly reflect the exercise that we are doing in this paper. Typically, when we think of the school choice problem, we try to analyze it as a matching problem. It's a many-to-one matching. We have schools on the one side, students on the other side. Students have preference rankings over the schools, and the schools have priority rankings. That's the setup of the school choice. Then we talk about a solution concept of stability. We say student-school pair blocks a matching if they prefer to be matched together, and the matching is stable if there is no such blocking pair. The many side of the school, side of the problem, that is the schools. If we define when we define stability, we assume that the school side have preferences over groups of students, and those are responsive to the priority ranking, meaning that the students are ranked, say, by an exam score or merit or any other criteria that reflects the objective of the school district. And then whenever a school prefers student 1 to student 2, this priority ranking translates to the sets of students as follows. If we have a set of students and we add student 1 to the set and then student 2 to the set, then the resulting set from the first one from adding 1 will be more preferred by the school than the resulting set from the 2, adding the second student. When there are distributional constraints, the problem is a little bit different. Against the students have preference rankings over schools and schools have priority rankings, but there are also distributional objectives. We may think again of stability as the solution concept that no student and school pair blocks the matching. However, in this case, the preferences of the many side is not responsive to the priority ranking. There are distributional objectives, so priorities do not have a one-to-one conversion to the school's preferences in this two-sided model. The solution, the common approach has been to assume that there are choice functions of the schools, and typically ad hoc choice functions, which do not necessarily reflect the policy objectives that the schools may have. But these school choice functions have been treated as the primitive of the model in the commonly treated as the primitive of the model in the previous literature. And the study of interest was the characterized properties of different mechanisms, given that these choice functions are already in place. In particular, substitutable preferences would guarantee that there is a stable matching. So with ad hoc choice functions, we may have stable solutions in the many-to-one matching. And stability is a key notion when there are strategic actors on both sides of the market. But it's not the policy goal for many problems, including potentially school choice. In the policy goal in school choice, we may think of it as eliminations of priority violations. We want to respect the underlying priorities of the school subject to meeting distributional constraints. When there are no distributional constraints, a stable matching eliminates priority violations. So it's an indirect way to achieve the policy goals in school choice. With distributional constraints, having the stability as the solution concept does not address the actual problem of eliminating priority violations. And so the The difference here in this work is that we do not assume a choice function for a school, but we want to come up with a desirable set of axioms that would describe a choice function. And secondly, we do not think of the choice of the school as the decisive component in the many-to-one matching problems, because we're interested in mechanisms and assignments. So we come up with natural properties or axioms on the set of mechanisms and assignment and try to see which choice, which of them satisfy those and what are the possibilities of achieving each of these distributional, each of these axioms. To summarize the related literature, as I said, there's a huge, rich literature on the topic. It's a very important topic, and there have been a lot of great papers addressing the question. And papers studying the two-sided problems, there's distributional objectives in school choice, like the ones here, do take stability as the solution concept, assuming that there is a choice rule for the schools without necessarily providing full axiomatic foundations for having such choice rules. Our paper is in the tradition of papers of works that introduce this axiomatic analysis of the school's choice problems. In particular, these papers come up with a set of axioms that would describe particular rules that are being used in practice, or a class of choice rules. We contribute to this strand of literature by characterizing giving an axiomatic analysis of the single school choice problem. But what we do more is that we take this to the general problem with multiple schools. So we study school choice, the controlled school choice setup, and we are trying to provide an axiomatic foundation for mechanisms in that setup. That second part of our work has no counterpart in the existing literature. It generalizes the axiomatic analysis from the single school problem to the general one. Let me start by describing the model and make things more concrete. In this work, we concentrate on the exercise of understanding, providing some axiomatic foundation for a single school's decision problem. This may be directly applicable to many priority-based assignments set up with distributional objectives, but we may think this may also be representative for school and college admissions when we have decentralized admissions. So each school has to choose its own students. We have a set of applicants and a single school with Q seats. Applicants are divided into types, and given our motivating examples, we may think of the type as being the socioeconomic tier of the student, or the low income versus high income status. For a subset of applicants, we use this A sub T notation to denote the subset of applicants from this set whose type is T. There is a priority ranking over the set of applicants. Again, going back to our example, we may think of this as the test scores, which is used as the priority for selective schools in Chicago and New York City. There are finally, there are type-specific reserves, RT, which will have the interpretation that some of the seats are reserved or set aside for beneficiaries of group T, type T. There are also, in the paper, we study another form of, another tool of affirmative action, which is the type-specific quotas. Well, in this presentation, we will ignore type-specific quota. They are accommodating and can be easily accommodated in the paper. The object of interest is a choice rule. We are given a set of applicants, and the goal is to choose a subset of these applicants, and subject to not exceeding the school's capacity. So the choice rule will be this object here, a mapping from the power set of applicants to itself, such that the number of chosen applicants does not exceed Q, which is the capacity of the school. We will come back to the full matching model later in the second part of the talk. In practice, the choice rule that has been implemented when there are distributional objectives is known as the reserved rules. And the idea is that it's an ad hoc method to transform the problem with distributional objectives to the purely priority-based assignment problem, which we know how to handle. We divide the schools into T+1 subschools. There is a school for each of the types. We call the school for type T, we denote it by S sub T. And there is an open school, which we denote by S sub 0. And the school ST, the subschool ST, has a capacity RT, which is the type T reserves for that corresponding type. The S0 school, the open school, has the remaining seats, so its capacity would be Q minus the sum over types RT. And the baseline priority ranking is modified for the schools for type T. So ST's priority ranking is modified in a way that elevates all type T applicants, and otherwise it is consistent with the original priority ranking. The priority ranking of the open school is not changed. Last component to describe the reserved rules is the application order. This application order would specify how we consider applicants for different subschools. So if we want to assign an applicant, we decide whether to choose an applicant or not. We may consider them for the different subschools, seats reserved for different types, and the order in which we're going to decide that we kind of do this is important. It plays a role in the final set of chosen student. And the object that we describe here is the application order, which says how should the agent be considered, in which order should the applicant be considered for different schools. And this is, of course, applicant specific, and it can be problem specific, depending on the set of candidates that we are choosing. We may apply a different application order. Remember that we are thinking of only one school, and by dividing the school into T+1, we kind of create a matching problem where this application order may be interpreted as the preferences and the modified priorities may be interpreted as the priorities. So then for each application order, we prescribe a reserves rule. And the reserves rule corresponding to an application order would be the outcome of the running deferred acceptance algorithm to this matching problem that we created. More specifically, for a set of applicants, we do the following. Until there are no rejections, we let an applicant apply to the highest ranked school according to its application order among those that has not rejected them. And each of the subschools considers all its applicants and accepts those with the highest priority according to the modified ranking and rejects the rest. As a result, whenever the procedure terminates, the union of all applicants assigned to all the schools would be the chosen set of students. So in the end of the day, we do not care in which sub-school or school the applicant is assigned, but we just mechanically count the applicants that are assigned to some school, and that would be the chosen set. Let me demonstrate the reserved rules through an example, through a simple example. We have 3 applicants, L1, L2, and H. We may think of L1 and L2 having a low income type and H having a high income type. And the priority ranking, the baseline priority ranking of the school is such that L1 is ranked highest, then H, then L2. The school has a reserves policy. It has 1 seat reserved for low income applicants. To implement reserve rules, we divide the school into 2 subschools. There will be no subschool for the high income applicant because there is no reserves for high income. There would be a 1 school, we'll call it SL. For the low income applicant, it would have capacity 1, and there will be 1 open school with capacity 1. The priority rankings would be modified so that low-income applicants receive the preferential priorities for the low-income school, but not the open school. If we may consider the following reserve rule corresponding to application orders when first everyone applies to the open seat, then to the reserve seat. In that case, first L1 will be chosen. If we run the reserves rule, L1 will be chosen as the highest priority applicant, and then it will she will be assigned to the low income seat, and then from H and L2 we have to consider. So she would be assigned to the open seat, and then from H and L2 we're going to consider one applicant to be admitted to the reserve seat, and that in that case that would be the low-income applicant because of the preferential priorities. The set of chosen applicants would be L1 and L2, sorry. And if we do apply the second reserve rules, in that case, all applicants would first apply to the reserve seat, and therefore L1 would be chosen by the reserve school as the highest priority applicant, who also has a low-income type, and then the open seat would be processed, and the open seat would be assigned to the applicant H2 as the H, which is the applicant with the highest priority. I apologize for the typos in the indexing. So the goal of this exercise is to demonstrate that different applications order do result in different choice rules. So what we described here is a class of rules, choice rules, rather than a single one. And we'll come back to this example later. The next goal is to, and this is now known in the literature. It's a very important considerations, and then known by the practitioners and in academia. We know that the reserves processing order does impact the outcome, and the literature has been thinking of these reserve rules as some general class of rules, though we believe this is the first axiomatic foundations of why we should even care, or what are the reserve rules accomplishing. We will show that there are a set of axioms that reserve rules satisfy, any reserve rules would satisfy, and therefore we may think that if these axioms are desirable, we may restrict our attention to the reserves rules. We will show that a subset of axioms actually uniquely pin down in the entire class of the reserve rule, and we show that this class still is not good enough, it's not tight enough, and then we impose a further axioms to get a unique rule that would be the solution of the problem. So some of the axioms are like very standard, and the first one is the reserves respecting. We want the choice rule to respect the reserves, meaning that for any set of applicants, it guarantees to choose at least up to RT applicants. So if there are less than RT applicants of this certain type, then all of them are selected. Otherwise, at least RT of them should be selected. Choice rule is non-wasteful. If for any problem, if it guarantees to select applicants at least up to the capacity. So if there are less applicants than the capacity, everybody is accepted. Otherwise, we need to accept at least 2 of them. In other words, none of the seats are wasted. To describe the next axioms, we'll give one more definition. We say an applicant A violates the priority of another applicant A prime at a choice rule. Then a problem, if the first applicant is chosen by this choice rule for this subset of applicants, the second applicant is not chosen, and the second applicant has a higher priority. In this case, we will also say that the priority of A prime is violated, or that applicant A causes a priority violation. The next axiom says that we want to eliminate priority violations within types. So whenever an applicant A violates the priority of another applicant A prime, then it should be that those 2 applicants are of different types. Eliminating these types of priority violation does not conflict with distributional objectives, and we impose it as an axiom. Finally, the last axiom, which is the new one and which gives the full characterization of the reserves rule, is the beyond reserves priority compatibility. This says that for each type, the number of applicants that cause priority violation is lower than the number of the reserves. We may think that whenever there are priority violations, which are unavoidable given the distributional objectives, we can explain those priority violations by that the applicants that cause the priority violations are assigned because of the distributional objective. Therefore, at least their type should not exceed, their number should not exceed the reserves, the distributional minimum guarantee. So the first result is that these 4 axioms give the full characterizations of the entire class of the reserves rule. Next, we argue that this class is very big. It has 4 criteria that we need to satisfy, but this may not, the entire class may not be desirable. In particular, one shortcoming with the reserves rule is that the order in which applicants are considered for different seats, different schools, depends on the problem in consideration. This would conflict with the substitutability property of the choice rule, which gives some consistency of how applicants are chosen across subsets. We say a choice rule is substitutable is if whenever an applicant is chosen from a set, then she is also chosen from a smaller set. And substitutability has been critical for stability in incentives properties in the mechanism design setting. We say an application order would support substitutability if the corresponding rule is substitutable. And the first observation is that if we fix the application order, we do not make it subset specific, but only applicant specific, then the substitutability will be satisfied. The question that we ask is whether this is necessary. And it appears no, that we need to something weaker, and in particular, we need not fully fixed application orders, but the application orders being fixed with respect to the reserved and open school may be sufficient. For each applicant, what matters is whether you apply to the open seat first or the seat reserved for your own type. And we show that this is necessary and sufficient to give substitutable choice rules. Then the next thing we do is that not only substitutability, but we are interested in stronger properties of respecting the policy objective in the school district. And by that, we actually pin down a unique choice rules, which we'll be calling the regular reserves rules. The regular reserves rules is very intuitive. We just assume that the application orders are such that every applicant is first considered or first applies to the school reserved for its own type. Formally, we'll say application order would be regular if the school for each applicant, the school of the corresponding type is ranked the highest according to this application order. There's a result is that if we fix the regularity of the rule, just saying that applicants first apply to the school reserved for their type, and it does not matter how they apply to the rest of the schools later, we will pin down the choice rule. So if two application orders are regular, then the corresponding choice rule is the same. The choice rule is uniquely pinned down. And we call the choice rule a regular reserves rule if it's a reserves rule for some and therefore all regular application orders. Let's go back to the example. We have 3 applicants and a single school with 2 seats. And we know that in this example, if we apply if we process the application to the open seats first, then L1 and L2 would be chosen. If we use another choice rule where applicants first apply to the reserved seat, then the open seat, then L1 and H would be chosen. It should be clear that This second rule is the regular rule, because the only restriction we put on regularity is that low-income applicant applies to their reserved seat before the open seat. And finally, note that L2 violates H's priority under Rule 1, but not under the second rule. We may think of the one second. So we may think of the regular reserve rule as in this example as the one that eliminates the priority violation, and this is done in a way that the distributional constraints of having one seat for low-income applicants are still met. Yes, there was a question?
Yes. So my question is, it seems like a very natural way to handle priority would be, we've got some mechanism like deferred acceptance, and it folks just apply to generally, and then you run it, and then if the outcome satisfies the reserve requirement, with just ignoring it, it's not binding constraint, then you're done. You just accept it. And so, which in this case, it would lead to the L1 and H being chosen. And I'm just wondering this, so applying, it seems sort of unnatural to apply to the reserve when the reserve might not actually be a binding constraint. I don't know if that makes sense.
Perfectly makes sense. In fact, yes, this example was just chosen as a very simple one when the reserves rule does not have a binding constraint, but it still may be binding. It may be that applying the regular rule will necessarily create priority violations, but it do so minimally. It will only do so if it's impossible to meet the distributional objectives otherwise. And this is exactly the argument like for the regular reserve rules. If the distributional constraints are not binding, why create priority violations? And why apply a reserve rule in the first place? If it's not binding, the regular reserve rule will always never create a priority violation. If the constraint is binding, it will do so in a way that minimizes priority violations. So applying the regular, and this is exactly the point against applying the alternative rules, because if the reserve requirements are already met by just priority-based assignment, then having the regular rule will not pose any distortions, as one are not needed. If it's needed to pose distortion, it will do so minimally. And this is not a specific for this example. That's a general result. It's a good transition. In fact, we show that among all rules that are not just reserved rules, but any rule that are reserved respecting a non-wasteful, the regular reserve minimizes the number of applicants whose priority is violated. If we also impose a larger class within those that also satisfy within type priority compatibility, the reserve rule will be the unique one that satisfies this property, and even a stronger notion of choosing the highest priority applicants. So let me give you one. So we may be interested in given motivated by the previous example. We may think of notice that other reserve rule may achieve a different distribution of different type T applicants. In particular, we characterize what this rule that accepts the maximum number of some type of applicants should look like, and the condition that we are getting is that type T applicants should apply to the open seat first, and all the other types should apply to the seat reserved for their own type. In this case, we'll accept the most of number of type T applicants. The question is, though, whether we ever need to apply such a rule, because if certain rule accepts a number of type T applicants, we can always increase the reserves, apply the regular rule, and achieve the same outcome with the regular rule. To summarize, the regular rule can replicate any reserve rule when reserves are adjusting, and unlike the other rules which do not have the axiomatic justification, any priority violations under regular rule can be fully explained by distributional constraints. So we think of the reserved rule, regular rule, applying the regular rule as providing a transparency in design and the implementation. We think that this counterpoints like a common approach in the literature, which takes the modified priorities as reserved seats as the model primitives, and then argues how we should process reserves, and noticing that it's an important policy consideration to fix the application order. We say no, we should not think of the application order as the policy tool because it's not clear what the objective that it achieves. The simultaneous choice of modified priorities and application order is a policy tool. Updating priorities is a means rather than an end. We should not think of it as a hard constraint. The question is, what are the actual policy goals and what we want to achieve? And then, if that is so, the regular reserve rule tells us how the application order should be applied. There is an important manifestation of the lack of axiomatic approach in the literature because there was no going back to the primitives of the model and the policy goals. The literature has been predominantly studying common application orders when two applicants apply to the seats, different seats in the same way. And this is restrictive. By doing so, in fact, we are excluding the possibilities of the regular rule and the type T maximal rule, which is very surprising if we look at the class of reserves mechanisms. And actually the one that we have been studying are those that do not have the axiomatic foundation. Let me now jump. So there's an important consideration here. The arguments for whether using regular or alternative reserve rule is a matter of transparency. We see that there is a clear trade-off. We either can expect more applicants from the beneficiary groups or create priority violations. And the question of which one you use seems like a political question rather than like a theoretical one. Actually, in fact, it appears that with multiple schools, there is no such clear trade-off. It's not that some rules generate better distributional outcomes, whether some respect priorities. It seems that the two of these goals can be achieved simultaneously in the multiple school setup. There is no such clear conflict, and we may have choice rules that are performing bad in both dimensions, whether there can be rules that are optimal, constraint optimal in these dimensions. And that's the goal that we are heading towards. Seeing the single school, the axiomatic analysis of the multiple school has a very similar flavor. We are just going to generalize this to a setup with many schools. One restriction that we put is that we need for some result, and there is a school with unrestricted capacity, but otherwise the schools have a capacity. Each of the school has its own priority ranking. There are type-specific reserves in every school, and the applicants have preference rankings over the schools. Think of the Chicago or New York City public school admission with distributional constraint. This maps almost exactly to the theoretical problem that we are studying. The assignment is a mapping such that the number of applicants assigned to each of the school does not exceed their capacity. Here are the equivalents of the axioms for the assignments from those that we define for the choice rule. We say an assignment is reserved respecting is if whenever an applicant is not assigned to a school that she prefers, it should be that the minimum reserves at the schools are met for her type. So it cannot be that there is a school that has reserves has not been met and an applicant is rejected from that school. Similarly, an assignment is non-wasteful if whenever an applicant is not getting into a school which she likes, then it should be that the school has been full. No seats are wasted. we define a priority violation instance as a triplet. It's a set of two applicants such that the first applicant prefers the school of the second applicant, and the first applicant also has a higher priority. This is the blocking triplet equivalent of our setup. We say an assignment is within type priority compatible if there is no priority violation instances among applicants that are of the same type. So to give a priority violations minimization result in this multiple school setup, we apply an ordinal notion of priority violations minimization. One natural notion would be counting the number of priority violation instances across different mechanisms and say which one is better. This may be too hard to restrict it, but we find we use an ordinal notion, which says that one assignment would priority dominate another assignment if the first assignment can strictly reduce the number of priority violations instances compared to the previous for the second assignment without causing more priority violation instances. Think of the Pareto efficiency as the ordinal notion of welfare, and this is the equivalent notion in terms of minimizing priority violations. We just say we cannot unambiguously improve upon reducing priority violations instances. And we say an assignment is priority violations minimal in a class of assignment, and if it's not dominated by any assignment of the class in this class. The preference ranking of all applicants, we refer to it as a problem, and the mechanism is a rule that gives an assignment for every problem. We'll naturally extend everything we say about assignment, all the axioms to S axioms for the mechanism. More specifically, we say a mechanism satisfies a certain axiom, and if for any problem, the corresponding assignment does so. Two more axioms for mechanisms. The first one is the standard strategy proofness. We say a mechanism is strategy proof if for no problem and no applicant, there could be an alternative preference report that improves the outcome of the applicant. An important policy goal for the school choice environment. And the next axiom is new to this paper, to the best of our knowledge. But the idea is the weak masculine monotonicity, and what we have here is something weaker. This will be useful for one of the characterization. So we say a mechanism is first choice monotonic if whenever we have a problem and we have the outcome of that problem by P, then if we consider an alternative problem where some set of applicants just rank this outcome of the first problem as their most preferred choice, then all of these applicants are receiving that same outcome. The idea is that if we change the problem, so if this mechanism selects a certain outcome, and if we change the problem so that the outcome is even more preferred by the applicants, it particularly is the most preferred choice, then the mechanism should give them the same outcome. We may think of that the mechanism thinks that the reason it chose that outcome for the first problem in the first place was that it was desirable. So if it was desirable and now it's getting even more desirable for everyone, we should still think that that should be the outcome of the problem. More specifically, we should think of this as some property that a lot of mechanisms satisfy, and it's logically it's weaker than the weak masculine monotonicity. Though it's not strong enough to pin down choice rules. It's yes. So the hero of today's presentation is the deferred acceptance with the regular reserves rules. We have two-sided matching problem where applicants apply to schools and schools tentatively accept applicants according to this the deferred acceptance process, also known as the cumulative offers mechanism. And the restriction that we have here is that all the schools apply the regular reserves rules when they are considering who to apply at a given stage. And here's the main characterization result. It appears that the deferred acceptance with the regular rules is priority violations minimal in the class of mechanisms that are reserve respecting, non-wasteful, and within type priority compatible. It's a very natural notion of minimizing priority violations, and the set of axioms that we have here are the minimal requirements in our setup, and it appears that deferred acceptance with regular reserve rules achieves this property. One important consideration is that the notion of priority violations minimality is may not be as strong as some other natural notions we may come up with, and however, there are like two arguments to say why this is a very interesting result. The first one is that if we think that the conditions are not easy to meet and there may be other rules that satisfy it, the answer is actually no. In the setup, when there are only two types, think of the New York City school admission, which is the largest school choice problem in the country. In that setup, there is a unique mechanism that is priority violations minimal among those that satisfy the basic axioms, and that are also strategy proof and first choice monotonic. The other argument is that we should be interested in this particular notion is that with other notions of priority violations minimality, we get a lot of impossibility results. I will come back to that in 2 slides, but let me give you some interpretation of the result and the characterization, the axiomatic analysis that we have in this paper for this multiple school setup. When there was one school, there was a clear trade-off between accepting more applicants from certain beneficiary groups or reducing priority violations. Our argument for using the regular reserve rule was that of transparency, predictability, and explainability. We understand what these rules accomplish. In the general setup with multiple schools, this trade-off is not even clear. It appears that if we run deferred acceptance with alternative rule, we may create more priority violations, but on top of that, we will not improve or change the distributional outcome. And on top of that, we may hurt the applicants. We will get an assignment that is priority dominated to the outcome of the reserve rule. In this case, what I'm saying in this environment, the conflict is not real. It's not that applying any reserve rule with either sacrifice or one or the other dimension. It appears now that the conflict is much less trivial, and it's a non-trivial result that we are getting a constraint optimality solution for the DA with regular reserves rule, which may be then a natural candidate for a solution in practice for these types of problems. Let me summarize maybe in the next 3 minutes or so, make one last point. And the idea is, the goal is to show that other notions of priority violations, minimality, give impossibility results. And we may not, unfortunately, we cannot say something more about the DA with regular reserve rule and for any mechanism for that purpose. We may think of assignment of priority violations, domination relations, according not the triplets inclusion, but the pairs inclusion. We may think of domination relation based on the applicants inclusion. And more naturally, we may think of cardinal notions of just minimizing the number of priority violations, as we did in the single school problem. We find that for these alternative notions, we get impossibility results. This is an axiomatic study of the mechanism. Let me introduce the last of the axioms. And that one is very informally stated here. We may think We may also want a mechanism to be computationally tractable, meaning that having a polynomial time algorithm that computes it. The first observation is that using this cardinal notion of priority violations minimality is not impossible to achieve by tractable mechanisms. And more formally, we show that finding an assignment that minimizes the number of priority violations among reserves and non-wasteful assignment is an NP-hard problem, even when there are two types. And if we look at the larger set of non-wasteful assignment, it's also an NP-hard problem. And more importantly, so this is not an economics argument for not having these properties. So let me make one, and that is that other notions of priority violations necessarily conflict with strategy proofness. No strategy proof mechanism is priority violation mechanism in the class of reserve respecting non-wasteful and within type priority compatible mechanisms for any of the notions of priority violations minimality, other than that of the instance defined as the triplet that we have been using. In the light of these negative results, our result of triplet inclusion may sound even cooler. We show that deferred acceptance with the regular reserves rule is reserve respecting non-wasteful and within type priority compatible. It is priority violations minimal in this class. It is strategy proof. It is first choice monotonic. It is the unique mechanism with these properties. And finally, it has a very simple description, highly practical, and computationally simple. To summarize, in this paper, we provide an axiomatic analysis of incorporating distributional objectives assignment problem. And we get a characterization of choice rules. We see that a set of axioms can actually pin down choice rules that the schools may use. And in fact, they may pin down a mechanism that can be applied. And the overall conceptual contribution is the transparent, explainable implementation of policy goals in market design.